Okay, in this video, we're going to go over a quick example of a conservation of angular momentum problem. So this one is with the spinning ice skater, and it's pretty common. So in this problem, we have an ice skater that's spinning with her arms outstretched. She has an angular speed of 0.782 revolutions per second and a rotational inertia of 2.52 kilograms times meters squared. She pulls her arms close into her body, and then the rotational inertia changes to 0.401 kilograms times meters squared. What is her new angular speed? So let's write down what we have here. So we have the angular speed, the initial angular speed of the skater. So it's omega initial, 0.782, and this is in revolutions per second. We will change that to radians per second, since radians per second is kind of the standard units for angular speed when we're working with angular momentum. So let's just multiply this by 2 pi. So when you multiply something by 2 pi, that's like saying radians per revolution. So that's one full circle, 2 pi radians, one revolution. And that way revolutions cancel out and you get radians per second. And so this is going to give us 4.91 radians per second. Okay, and so we also have the initial rotational inertia. So that's I initial. And that's 2.52 kilograms times meters squared. And then they also give us the final rotational inertia, and that is 0.401 kilograms times meters squared. And so we want to find the final angular speed in radians per second. So what we can do here is use conservation of angular momentum. So angular momentum is given by this capital L, and that is just the rotational inertia times omega. For both the initial and final situations, these are equal. So that means I initial times omega initial equals I final times omega final. So this is the initial angular momentum equal to the final angular momentum. So we want to find omega final, so let's just divide both sides by I final. That's going to give us omega final is equal to I initial omega initial divided by I final. So we can just plug in these values here. So that's 2.52 kilograms times meters squared divided by 0.401 kilograms times meters squared times omega initial, 4.91 radians per second. And here our units for the rotational inertia are going to cancel out, and this will be in radians per second. So this gives us omega final is equal to 30.9 radians per second. So it's increased quite a bit when she pulls her arms in. So hopefully that was helpful. We'll do some more of these angular momentum problems. There's a lot of different types of questions that can be asked about this. So let me know if there's anything else you guys would like to see, and thanks for watching.